Good afternoon. My name is Segal. I'm the principal product architect for Akamai's cloud security business unit. With me, I have Tsvika Klein, product manager for the cloud security business unit as well. We're going to talk about big data intelligence. So we have a few topics that we need to cover today that are a bit orthogonal or seems like not really related to each other. But they will all lead us to the last topic, which is the core rule set, and so I'll get to it in a second. So first, we're going to start by talking about Akamai and the relationship between Akamai and the OWASP mod security core rule set project. Why are we here talking about this project? What gives us the right, other than OWASP, to stand here and talk about this project? Then I will hand it over to Tsvika to discuss security big data at Akamai, a very interesting platform that we've built to collect big data. Then we'll get back to talking a little bit about WAF. We'll talk about how you measure accuracy properly and scientifically. We'll talk about precision, recall, accuracy, and so forth. And then that will lead us to talk about the core rule set project and how we see it through the big data prism of the platform that Akamai has built. What we've learned, what works, what doesn't work, how we change the project to fit Akamai's cloud-based WAF model. But we only have 45 minutes and a lot of topics, different topics to cover, so we had to go wide and shallow. We couldn't go very deep and very technical in each direction. So if you have technical questions, come. Don't worry about bothering us. You can catch us later or tomorrow and ask us the more technical questions that you might have. So let's spend a few moments talking about Akamai and about the core rule set and the relationship between them. Now, this is not an Akamai marketing pitch. I'm not trying to sell you anything. Yes, we have a terrific platform, but that's not why we're here. However, I do have to mention what Akamai does, why we have this big data, how we are related to the core rule set project, and so forth. So we will spend maybe 2 slides talking about the platform itself, not trying to sell you, again, any products. So Akamai has been offering a cloud-based application security solution. Part of it is a WAF since 2009. The flagship product is called the Kona Site Defender, which includes part of it includes actually the web application layer protection includes the OWASP core rule set rules within it as a part of what we call the Akamai Kona rules. They are the core rule set rules, around them some Akamai rules and other protections that are pretty much out of scope, and just going to quickly go through them: DDoS protection, DNS protection, bot detection, site cloaking, and so forth. I just want to mention that when I do talk about the core rule set project and the rules, Akamai does not embed mod security itself. There's no mod security code within the Akamai platform. We merely ported, with the help of Ryan here from, I remember Bridge, but Trustre, thank you. So those are the rules that we're basically running on top of the Akamai code. And now I'm actually going to give it over to Tsvika to talk about the security big data, and I'll be back in a few minutes.
Hi, everyone. Thanks, Ori. So first, I'd like to give you a quick introduction about Akamai. Akamai provides fast, reliable, and secure web user interface from any device anywhere in the world. We have over 120,000 servers spread in over 2,000 locations in 82 countries, delivering internet traffic for our customers. Just think about the magnitude of this platform. Let's look at some facts about this magnitude and size. First of all, Akamai handles over 100 million page views per second and 500 billion hits per day. We see over 700 million IP addresses every quarter. We see pretty much every user that accesses the internet at least once in the course of 1 month. We collect about 260 terabytes of compressed logs every day. We have visibility to 30% of all internet traffic. Just think about how much traffic flows through this platform. Now, we have the Kona security solutions that Ori mentioned. These security solutions create security events over the platform. We had to build a big data platform to grab all these security events so that we'll be able to analyze and provide services on top of this data. For this, we built a platform that we named CSI, which refers to Cloud Security Intelligence. The platform handles 10 terabytes of daily attack data. We store 2 petabytes of security data for a duration of 45 days. The platform is capable of receiving 140,000 concurrent connections from all the edge servers that are spread around the globe. Every second, we analyze 600,000 lines of security events. Every day, we run 8,000 queries on top of the data that we store for applications that are running on top of this platform. Let's take a quick look about a high-level overview of the architecture of this platform. The platform receives all the security events from all the edge servers around the globe. We have the log agents that receive this event and store it in our distributed computing platform that is based on Hadoop and HBase. We build our own query language that we name Yoda. We called it Yoda pretty much because it has an answer for everything. We have all these applications that are running on top of this data. The applications are divided to a backend application and a front-end application. The backend application interacts with the data through RESTful API. We decided to build our own query engine for several reasons. First of all, the query engine that we built is interactive, meaning that we can see the progress of each query that we run on the platform and see how the data is accumulated through the platform. This is very different from other query engines where you also only run batch jobs and you wait until the job completed before you see any results. So we can really monitor the progress of every query that we run on the platform. We also built the query engine in a way that will be able to run several questions on one pass through the data. So we use multiple data streams to save the number of times that we actually have to go through the data. And this obviously increases performance for our platform. We build an intuitive query language. So instead of just using Java code, we actually provide XML-based queries that are really SQL-like queries. And we also have the ability to incorporate Java code for complex logic. And the last thing I want to talk about regarding the query engine that we build is high cardinality. Just think about the data that we store. It's internet traffic. We have all these IP addresses and user agents, for example, that have really high cardinality. And once we run queries on top of this data, we really need to do it in an efficient way. For that, we build the system so that we'll be able to handle this high cardinality and aggregate the information so that we'll get top results on this information. So now with all this platform that we build, let's talk a little bit about the challenges when it comes to a big data platform, especially in regard to security. So the first challenge is all about finding the needle in a haystack. It's really going through all these huge amounts of data that I talked about and drilling down to the specific security events that can really help us to solve the problem that we are facing. The second challenge is harnessing the information in order to see the bigger picture. Think about it as zooming out of the data to actually see correlated events. See, for example, when a specific industry sector is being attacked, or if there's a nationwide attack, again, one nation against another nation. For that, we really need to look at the data by zooming out of it, like looking at all the data. You can also see that these two kind of challenges a little bit contradicting. One is talking about zooming out, and the other one is really talking about drilling down to the specific events. So it feels like there's some kind of contradiction here. We built an application to really address these specific challenges. We named the application Sarah, which is basically our security analytics and research application. This application is used by our internal users, professional services, and research to really go through the data and analyze the data that we store. So first of all, it gives a broad visibility to all the rules that triggered in one or more customers. And then with just 6 clicks of a mouse, you can really drill down to the specific events that cause the rule to trigger. So you can see that we really, with this application, we really address the 2 challenges I talked about. First of all, zooming out of the data, looking globally on what is going on in the system, and then drilling down to the events that can really help us identify what was the cause of this. And we use these applications to also analyze the core rule set. And at this point, I'll turn it back to Ori to talk a little bit about WAF and CRS.
Thank you, Tsvika. Now let's get back to talking about WAF and later on about the OWASP core rule set project. So we talked about why we're here. We talked about the big data platform that helps us to collect this data. I now want to spend a few slides or a few moments talking about how to measure properly and scientifically the accuracy of a WAF product and of the core rule set specifically. So I want everybody to imagine the best WAF you can imagine, a WAF that is able to block all possible attack vectors, from process scripting to SQL injection, response splitting, you name it, that WAF will block it. I'm sure that everybody would like to buy such a WAF, right? Now, what happens if I told you that this WAF is basically blocking 100% of the HTTP requests, both valid and invalid? Suddenly, this WAF is not such a big deal, right? So when you're coming to talk about the accuracy of a WAF, or measuring the accuracy of a WAF, or a deployment, a specific deployment, you have to take into consideration 4 very basic terms. The true positives, which are basically the real attacks that you block, good thing that you're doing. The valid request that you allowed through, again, a good thing, okay, those are the true negatives. How much valid traffic, was inappropriately blocked. So good users trying to get through, getting blocked. Those are the false positives, right? And then how many attacks were allowed through? Those are the things that you missed, the bad things that your WAF did not respond to properly. So those are the false negatives. Now that we know the basic terms, let's take a look at what we can do with them and how we use them in a more scientific way to measure the accuracy. So we'll start by precision. Precision is the ratio between, and you can see it here, true positives, the attack that we actually block, divided by the attack that we blocked and things that we blocked that we didn't have to. So basically, the percentage of blocked requests that were actual attacks. If you think about it a little more, if you are a WAF customer or an admin that is worried about blocking valid traffic, you should be worried and look at the precision ratio. You need to have a very high precision ratio to make sure that your WAF is only blocking attacks and not valid traffic, right? Recall, on the other end, is the ratio between true positives, again, the attacks that you block divided by all attacks, the true positives and those that you've missed, the false negatives. Basically, the ratio or the percentage of attacks that were actually blocked. This is how secure your WAF is, what kind of security protection it's actually delivering, right? Sort of a sensitivity, security sensitivity. A customer or an admin that is worried about blocking attacks, that really wants a secure WAF, would want the recall value to be very high, or close to 1, obviously. Now, for both things, for both precision and recall, you want the highest value possible. But at some point, there is a balance that you need to do. So the more security protections you're adding, the more you're likely to block valid traffic, unless you're very good at doing this. So at some point, you're raising the precision and recall very high, and then you have to start thinking, okay, what do I want to do? What is more important for me? Do I want to block all attacks on the expense of valid users? Or I'm willing to let a few attacks go through, few requests go through, but allow good users to actually use and make use of the functionality of the application. Now, in order to have one number to measure everything, there's the accuracy formula. Accuracy is basically the percentage of decisions that were good decisions. How good is your WAF in making security decisions? On the top part of the equation, you see the true positives plus the true negatives. Those are everything good that you've done divided by all the decisions that you've done. There is a problem with this formula. The problem is that if the sizes of the groups is very, very different in size, for example, in the real world, in the WAF world, the number of attacks is really, really small by orders of magnitude than all of the HTTP traffic that is going through the WAF, right? In those cases, a WAF that doesn't work very well, that doesn't block the little attacks that go through it, will still have a high accuracy if you use this formula. So in order to help us with that, we use what's called the Matthews Correlation Coefficient, MCC. This is a correlation coefficient between WAF decisions and actual nature of requests. Like most mathematical correlation coefficients, a value of -1 means that your WAF is deciding in complete contradiction to reality. So a good request is getting blocked and a bad request is allowed through. A value of 0 means that your WAF is basically randomly predicting what to do. It's not very good at protecting. And a +1 means that your WAF is in complete correlation to reality. So attacks are getting blocked and valid users are allowed through. So let's take a look at some examples of different WAF types, different WAF behaviors, and how their precision, recall, accuracy, and MCC looks like. So we'll start with an example of a realistic WAF. In all of my examples in this page, I have 1,000 HTTP requests, out of which 990 are valid requests, and 10 are attacks. This realistic WAF actually blocked 11 attacks, or 11 requests, out of which 8 were true positives, attacks that were blocked correctly. Out of the 990 valid requests, 987 were allowed through. So we had 3 false positives, it's not bad, and 2 false negatives, 2 attacks that we missed. The precision in this case is 0.73, the recall is 0.8, and the accuracy is pretty high, 0.995. Very much in alignment with what I mentioned earlier, that if the groups are very different in size, then the accuracy is very high. This is not the best WAF in the world, yet it got a very high accuracy rate. So here we can actually take a look at the MCC rate, which is 0.76, which gives us a very good measurement of how this WAF is behaving. On the other hand, we have a WAF that's shut down, it's off, it's not blocking anything, everything is going through. So again, 1,000 requests, 990 valid, 10 attacks, we didn't block anything, everything went through. The true negatives is 990, so everything that was valid was allowed through, which is very good. But all the attacks, we basically missed all the attacks, and we had 0 false positives because we didn't catch anything. So in this scenario, you can't actually calculate the precision. The recall is 0 because we're not very good in securing the site, right? And weirdly enough, the accuracy is higher. It's 0.99, again, because the difference in size of the groups, So here again, I'm looking at the MCC, and if you calculate it, it's actually 0, meaning that this WAF is predicting randomly, It's not a very good WAF. So here, we're actually looking at the precision, recall, and MCC in order to understand how well this WAF is behaving, And behaving not only with attacks, but as well, at the same time with valid traffic, which is very important. On the other end of the spectrum, we have a WAF that blocks everything. Trigger a happy WAF, nothing goes through. That's the one I mentioned earlier a few slides ago. So I caught all the attacks, so 10 true positives. I don't have any true negatives. I have a lot of false positives, 990, and 0 false negatives. The precision is very low. This WAF is generating a lot of noise, blocking and blocking valid requests. And the accuracy is very low, and the MCC, again, this WAF is behaving randomly. So I have a couple more examples, but because we're short in time, I'm just going to go over them. So when coming to talk about WAF accuracy, it is very important to bring into the discussion not only the attacks that are being blocked, but also how good are you in allowing valid traffic through. And this is something that I'm not hearing enough in discussions. Usually, when pen testers and consultants try to evaluate the WAF, they will run a scanner through the WAF, they will send attacks, and they will tell the WAF owner or the vendor, your WAF is blocking attacks, it's missing a few attacks, it's good in SQL injection, it's bad in process scripting, etc. But nobody's talking about how well is this behaving with valid traffic. When I deploy your WAF, how many good users are going to get blocked just because your WAF is trigger happy, for example, okay? So talking about a WAF accuracy only by the rate of attacks that it's blocking is not relevant anymore. So getting back to the core rule set, in order to assess WAF accuracy and a core rule set at Akamai, we built what we call AWT, the Akamai WAF testing framework. This is a framework that allows us to assess the accuracy of both valid traffic and attack traffic and give us all the statistics that I just mentioned. And you'll see in a second also help us to assess what is working and what is not working with the core rule set project. So AWT as a framework has an ability to send both valid traffic and attack traffic. So it's not a scanner, it's not a web application scanner, it's not app scanner or web inspect. It does have the capability to send attacks or prototypes of attacks, but it also is able to send valid user traffic into the system. So emulate real valid web interaction with the site behind the WAF. Now, in order to have thousands and thousands of test cases, because it's not enough to send 100 or 200 test cases, right? That's not statistics, that's not big data. We had to either create or collect thousands of HTTP requests, both valid and invalid. So how did we do that? We created 3 ways for us to add, to quickly add test cases. So first of all, this AWT platform receives AWT files. Those are basically raw text HTTP traffic inside the text file. So you can basically author the file or edit the file with Notepad or whatever you like editing with. We also created a burp proxy extender that allows us to record traffic to websites, record live interaction to the website, and export the live traffic and only the interesting part of the traffic, only the interesting requests, those with parameters and cookies and weird headers, and turn them into AWT test case files. And last but not least, we created something that ports pickup files, sniffer files from Wireshark that allows us to record traffic not only from browser but from any kind of web client and port them and turn them into AWT test files. These mechanisms allowed us to import a lot of test cases from the same platform that Tsvika mentioned earlier, the Akamai CSI platform, the Cloud Security Intelligence. We made the platform very configurable, so it can work with any WAF out there. It can work with the Akamai WAF, but if you really want to test the Incapsula WAF or the Cloudflare or Imperva or whatever, you can use it to do that. You do that by actually defining how would a success or a fail criteria look like. And it generates very intuitive XML reports. Intuitive and XML is a bit of an oxymoron, but intuitive HTML reports, which you'll see in a second. And these reports actually allowed us to debug the rules from the core rule set. Based on this, it allowed us to see the false positives, the false negatives, precision, recall, and to debug anomaly scoring, which is kind of a new thing, at least for Akamai, that's coming from the core rule set 226 and north. You will see, I will talk about rule combinations and rule triggers in the context of anomaly scoring in a second. So a testing framework without test cases is not very efficient, so we needed to collect all of that traffic that I mentioned earlier. So where did we get the traffic? We started with the good traffic. So we recorded web interaction on most of the Alexa top 100 internet sites, ranging from commerce to health, consumer electronics, etc. We recorded these interactions, some of which was through a crawler, some of which was from manual interaction that we've done. And then we also ported a lot of false positive test cases. We took requests that triggered false positives from the Akamai platform, from the big data platform that Tsvika mentioned, and we ported them into this system. And we also ported some valid test cases from other similar tools. Earlier this year, Imperva came out with a similar tool called WTF. We tried to use it in the beginning, and then we decided that we need our own tool because it was lacking a lot of the functions that I mentioned earlier. Calculations of statistics, ability to port a lot of test cases, do it quickly, and so forth. So we built this tool, but we allowed ourselves to bring in tests from other tools as well. For the bad test cases, for the traffic, the attack traffic, we actually recorded commercial web application scanner traffic like IBM AppScan and WebInspect and Nessus and all those scanners that you know. We also ported traffic from Havij and SQL Map, all the attacks from these SQL exploitation frameworks. And we also brought in, again, attacks, real attacks that we found within the Akamai CSI platform. And of course, exploits coming from the internet, from fuzzers, FuzzDB, ExploitDB, and so forth. All in all, we gathered tens of thousands of HTTP requests, divided sort of 95% valid traffic and 5% attacks, which gave us a good starting point to start and see, okay, what is going on? How is our WAF behaving? How are the rules really behaving in reality? This is how the report looks like. So it starts with an executive summary. You see the amount of requests, the attack traffic, the valid traffic, false positive, false negatives, precision, recall, accuracy, MCC, everything that I mentioned earlier. Very graphic, very easy to navigate. Then for each attack type, you can see here how many false negatives and true positives we have. How good are we in each of those different attack types? So for Havij traffic, from local file include, for cross-site scripting, we knew where we're doing good and where we're not and what needs to be analyzed a bit more deeply. If you're thinking about WAF rules, you have the capability to drill down and see which rules are contributing more to false positives. And not only that, you can actually see, and this is important, very important for the core rule set project anomaly scoring, we can tell which rule combinations contribute the most to false positives. In anomaly scoring, a few rules are running and contributing score, right? So we can see which combinations of rules tend to trigger on what kind of sites. We can see not only rule combinations, but also sub-combinations. So this helped us to go and focus on certain rules and see that these rules have some problem that we need to solve. And we'll see a few examples of that in a moment. So now that we know how we can measure WAF accuracy, how you measure WAF accuracy, what tools we have to measure WAF accuracy in the big data platform, let's see of what we've learned about the core rule set project from all of this. So we start with what I call the issues called risk groups. The core rule set 2 to 6 that we used actually use it's almost a single anomaly score. So there's one pile of scores that go. Every rule that triggers contributes to this score, and then you have a threshold, and when the score exceeds the threshold, you block or you trigger an action, right? This is how things work. What we notice is that our customers, they're not interested in seeing the score was 45 and there was a bunch of rules that triggered. They want to know what really happened. Was it a SQL injection attack? Was it an RFI? Was it a cross-site scripting? And having one pile, of scores with a bunch of rules with numbers that appear there wasn't giving them the granularity and the visibility that they needed. So what we decided to separate the anomaly scoring accounting to smaller, what we call risk groups, the attack types. This gives you a clear understanding of what happens. So you have a score for cross-site scripting, you have a score for SQL injection. Those actually exist in the core rule sets, but at this point, nobody really uses it. We added more risk groups, RFI and LFI and command injection and Trojans, etc. There's, I think, 9 or 10 different risk groups. And now the challenge is that each rule has to be mapped to one or more of those risk groups. So there are rules that can contribute to more than one risk group. For example, a rule that looks for, semicolon can potentially contribute to SQL injection, but also to cross-site scripting. So we had to go through the entire core rule set and start mapping each and every rule to the different one or more risk groups that we created. This requires a lot of attention and much more thought into anomaly scoring as a concept. You no longer pour all your score into one place. You don't bolt scores on rules, which is sort of how the core rule set project evolved. We added, right, Ryan, we added anomaly scoring to the project, but there's more things that need to be done in order for this to be fully tuned, at least in our opinion. On the same topic of thresholds, it appears that it's not a one-size-fit-all kind of situation, the threshold, the anomaly score threshold. Let's take a look at an example. This is a very basic cross-site scripting probing attack, the alert script alert, the script alert script that we all know. And this, if you take the core rule set vanilla kind of project, would probably yield a score of, I think, a 30. That's what happened when I ran it. So if we're a bit in a panic mode and we need some buffer, we will set our threshold to 25. This assures us that every cross-site scripting out there will be caught, right? Now, somebody comes in and slips in a command injection attack. This is a very classic attack. You call bin shell cat etc pass wd. This triggered only one rule, a very important rule, but this rule contributed only 5. I failed to mention that earlier. The score of 30 came from 6 different rules, at least. So 25 doesn't work anymore. We have to lower the threshold, right? So we lower it to 5. Now a good valid XML traffic goes through and triggers only a couple of cross-site scripting rules, giving it a score of 10. This triggers a false positive. And why is that? So this is a way to sort of visualize the problem. You have one threshold and many different attack types. The threshold doesn't work for all of them. If you set the threshold at one point, something has to give. Some attack types will have false negatives, some will have false positives. So there is a way around it, which is not what we decided to do, which is to break it down into risk groups. You can theoretically modify the score of each rule to fit the single threshold. That works, but it requires a lot of work, and it's not standardized. So the core rule set uses scores of 2 to 5. So we decided to go ahead with the different risk groups concept. The next item on my list is HTTP violations. And this is a very interesting thing. It appears that HTTP protocol violations generate billions and billions of triggers on an untuned system. You know, the idea behind it was good. We tried to enforce, so the project tried to enforce HTTP RFC. But today, 10 years after, you have very weird clients sending very weird HTTP. You have clients accessing APIs, RESTful web services, RSS feeds, you have bots, and all of those fail to adhere to valid HTTP. So they don't send headers, they forget to send things in the right order, they forget to send content type when they have a body for the HTTP request, and so forth. Everything happens. You can assume that everything happens. Every single rule there triggers. But we looked at I think a few weeks of triggers on an untuned system. We actually had 70 billion triggers, out of which 14% was for the rule 960015, which is a request missing and accept header. This is huge. We see it on untuned deployments all the time. And it's really, you will see in a second why this happens, but it's not bad. It doesn't deserve to be blocked. Then the missing user agent, which again happens. So the bottom line is that you can't really trust the HTTP violation rules on their own. What we did is we created an invalid HTTP risk group, and we gave it its own threshold, and now we only block the seriously damaged HTTP requests, those that are really missing things or look really bizarre. And of course, for catching all those DDoS tools and all the bad bots, we actually created a more focused tool fingerprints or rule fingerprints. Now let's take a look at why request missing accept header is one of the rules that triggers the most. And this is an example of how we use the big data platform that Tsvika mentioned earlier. So I took 3 hours of triggers of rule 960015, the request missing accept header, and I wanted to see if I can find what is causing this. So I asked the system, which URLs tend to trigger this rule the most? And the answer I got from Yoda, from our platform, was that 85% was coming from triggers on static media files. Those are cascading style sheets, JavaScript, static HTMLs, JPEGs, PNGs, all of those static media files. I then thought to myself, hey, maybe there's a couple of browsers, stinky browsers, crappy browsers that are forgetting to send the accept header. That would be cool if I can find a few unique browsers that are causing all this problem. Sadly, in the span of 3 hours, I saw 95,000 unique user agents. Unique. So the theory of catching a few browsers, didn't really go through. So I asked the system, is there anything else in common to all those unique user agents? still trying to see whether this is has to do with some browser out there. And what I saw is that 50% of the triggers had the word Android within the user agent header. Now it's starting to become interesting. So I asked the system to give me a little bit more, give me statistics about what is common to all those, again, unique user agents. And what we saw was that, again, 50% was Android, 20% out of it had the string Apple WebKit, so some client that is based on the Apple WebKit render. 21% had the word news aggregator. I had to remove which sites are actually causing this, but major news sites have their apps that are not sending these headers. And then the word app. So all in all, what we've learned from this is that mobile applications, mobile browsers, forget to send or don't send the accept header, especially when accessing static media files. And this is a good example of what we've done or what we can do with this system in order to research all sorts of weird rule behaviors. So next item on my list is cookies. So we noticed that cookies tend to generate a lot of false positives. And we tried to understand why is this. So if you look at cookies in 2003, 10 years ago, they were very simple. You had a name equals value, and it was very easy to spot a SQL injection attack or a cross-site scripting attack or if something is weird. On the other end, if you fast forward 10 years, 2013, this is how cookies look like today. This is a real cookie that I took from an Akamai customer, anonymized, obviously. Everything is here. You have pipes, and you have what looks like Unix commands, and things that look like SQL injection and JSON objects, and even JavaScript within XML inside a cookie. So good luck with trying to catch SQL injection using signatures on this and cross-site scripting, etc. So what we've learned from this is that first we have to quiet these down and do it in an intelligent way. So you can create rule exceptions, or you should create rule exceptions for certain rules not to trigger on what I call complex cookies that have complex values. The other thing that we recommended that at some point in time, mod security will allow custom parsers that you can write to help analyze more custom or complex cookie structures and run the rules on the right parts of the cookies. The next thing that I want to discuss is what I call a score that spreads across selectors. What we noticed is that in a lot of the false positive scenarios, especially for SQL injection, you see a very high score for, let's say, SQL injection or cross-site scripting, but it spreads across different areas of the HTTP request. So here you see actual cookies from a request to an Akamai customer. There are 4 cookies. I titled them or named them C1 to C4. Not a good name, C4. And you see a few rules triggering on each different cookie. So a few rules triggering on cookie C1, like 950.901, contributing 5, and then a few rules on cookie 2 and cookie 3 and cookie 4, a total of score of 18. Now, if you look at it from very high level, you say, okay, there's score 18, it passed the SQL injection threshold, I'm going to block it, it's a SQL injection. But if you look closely, you see that you have some scores sprinkled here and there and there and there, and that's not how an attack looks like. When you do a SQL injection attack, you usually concentrate on a single parameter or a single cookie, and there you inject your exploit. Yes, there are situations and applications where that's not true, where you can split, for example, with parameter pollution, but then it's the same name, parameter name. But I can imagine that there are some apps, and there are, I'm sure, where somebody will glue together 2 parameters or 2 cookies and put them in a single query, and in some bizarre way you can exploit that. But in most cases, what we see, we see that when that happens, when that scenario happens, it's almost certainly a false positive. This allows us to go back to the big data system and say, bring me all the triggers that triggered or tripped the SQL injection anomaly threshold or passed the threshold where the score was very high, but it triggered on many different selectors. Take all of that and throw it out the window. We don't want to look at it. So, sorry. I think that the CoralSet project should consider some sort of a heuristic like that. maybe as a rule, as a summarizing rule, something that looks at the different, or how the score is spread, and consider maybe marking these as potential false positives. The last item on my list is what I call rule inefficiency. So during the big data analysis that we ran, all the AWT scans and the big data analysis that we've done, we noticed a few troubling issues with the core rule set rules. The first thing was that many rules had redundancies in the regular expressions. This happens, I think, this is my assumption, because different rules came from different people, different groups, different contributors, even different projects. So some rules came from the PHP IDS project, and they have different quality, different accuracy levels, and some of them have some redundancies between them. And this is a problem because it tends to push the score up when something happens. So when you see, when there is a false positive, this false positive is doubled or multiplied because there are many different rules that look for similar redundant things. And this behavior forces our professional services folks or the people who's configuring the WAF to push the score, the threshold up, so we don't pay attention to these false positives. But then we have to start missing other attacks that have a lower score, right? The other thing that we noticed is that some rules combine weak and strong expressions. So as an example, we noticed that a rule that looks for apostrophe semicolon was merged together with an expression that looks for select something from something where something, which is obviously a SQL injection attempt, very blunt SQL injection attempt, right? Now, this rule kept triggering false positive because a semicolon, an apostrophe semicolon, something that happens a lot in cookies like you just saw. So we had to reduce the score for that rule, but then that would hurt the very accurate expression in the same rule. So what we had to do is we had to yank out of the rule the bad or the low quality expressions, give them either their own rule or just throw them away if they weren't needed. Yeah, and the last but not least, we noticed that a few rules were useless. I gave an example of here, rule 981172, which is the rule that looks for, I think, 8 and above some weird characters that you saw earlier. What we noticed, and this is using the AWT reports, I talked about rule combinations, is that some rules, like this one, when they contribute score, they never help us to pass the threshold. The threshold was already passed for actual attacks. But for valid traffic, they always get us to the point where it's a false positive. So by disabling these rules, we got the same rate for in catching attacks for true positives or false negatives, and we reduced the amount of false positives, the overall false positives of the system. So it's going to be hard to summarize the talk because we had many different scattered topics here. I'll try to do my best. First of all, about big data, and I think it's obvious, but we think that mod security, the core rule set project would benefit from having anonymized trigger information. And we know that nobody is going to, not nobody, but some organizations are going to opt out unless they can be proven that we're not stealing any good information. But this would greatly increase the accuracy of the project and of the core rule set. With regard to the future, obviously Akamai has already contributed to the core rule set project. We will continue to contribute. We want to contribute back to the core rule set project. But at this point, we highly recommend, because we really diverge from the project itself, our rules are no longer, they no longer look like the core rule set. We have our own risk groups and our own modifications. And in order to be able to contribute back, we actually need OS core rule set to adopt some of these concepts. It will make it easier for us to actually contribute back to the community. With regards to WAF testing, as I mentioned, I think the industry has matured to the point where a discussion about WAF accuracy has to take into consideration precision, recall, accuracy, MCC, all of this. It's no longer, it's not right. It's no longer the point where we can just say, I ran a scanner, you missed a few cross-site scripting, your WAF sucks. That's not good enough. Maybe my WAF sucks at missing a few cross-site scriptings, but that's because I'm allowing all of the good users through. So you have to consider both, not just running a scanner. And with that, I'd like to thank everybody for coming to this presentation, and I hope you enjoyed it. And if there are any questions, I think we still have at least 5 minutes, or you can catch us in the corridor or later on. Yeah. I'm not sure if I heard the question. So working on live data meant that we had to put it in front of a site, and we wanted a very wide range of different traffic. Yes, we can record or set it to record traffic to Akamai customers from a wide range of customers. That's what we tried to do. It doesn't really matter if it's traffic from 2 weeks ago or from now, okay? But this is, yes, this is the idea. We're going to capture a lot of valid traffic and put it into the system. We can do the calculations in real time. Yes, it doesn't contradict. Did that answer you? So come talk to me afterwards, sorry. Other questions? Great, thank you for coming.